Your parents are disappointed in you, but you could turn all of that around by learning data engineering in about a month by following this really elaborate roadmap. Now, this is a very detailed roadmap, but much like when you're on the hub, I am going to help you skip to the best parts so you can keep this experience short and sweet. Data engineers stand on business, but data engineering stands on Python and SQL, and you will unfortunately need those as prerequisites before you even start to think about this. Now, to get started, you will need to pick a lane or a programming language, and unless you like punishment and torturing yourself, just go with Python. And once you've learned Python, learn data structures and algorithms just enough to make yourself dangerous, learn Git and GitHub so you can play nice with your friends and teammates, and learn the basics of Linux networking and distributed systems. That's going to come in handy later on. Being a data engineer is like being a parent to many different kinds of data, so you have to understand the life cycle of data and the pains and challenges that come at each stage. And much like parenthood, some data is planned, some data isn't. There are many sources from which you can get data, and you have to understand the nature of these sources and the nature of the data that comes from these sources. But once you have data come into your home, you have no choice but to give it a roof over its head and to raise it, aka you have to figure out the right database solution for the data you're dealing with. Now, as a software engineer, you get to make the choice. You get to choose to be a rational person and go with relational databases, or you could choose to be the clown prince of crime and go with NoSQL databases. But in the world of data engineering, you have to understand both of these database technologies really well. What's that? Okay. So my lawyers are telling me I can't needlessly knock on NoSQL databases like that, so let me give you a quick rundown of the pros and cons of each of these technologies. Relational databases offer really good performance, particularly when you have complex queries, and they offer great consistency. Even if you're looking at two database instances at different parts of the world, you're always going to be getting the same version of data at any given time. However, relational databases do slow down at scale. NoSQL databases, on the other hand, offer really good performance for simpler queries, and they scale really well horizontally. Meaning, if you add more and more database instances to your database cluster, the query performance is going to get better. However, NoSQL databases do offer what is called eventual consistency, meaning that if you're looking at your database cluster at any given time, depending on which instance you're querying, you may be getting different versions of your data. Relational databases are very picky and stubborn, and you can think about adding data to relational databases as if you were feeding it. For example, if you were feeding a dish to a relational database and any of the ingredients are off, it's going to throw up the entire dish. This is called data validation. If you've laid the table with multiple dishes as part of the meal you're offering to a relational database and just one of the dishes is off, it's going to flip the table and storm out of the room. This is called a transaction block. If any one of the transactions in your transaction block fails, the relational database is going to reject the entire transaction block. But you can get a relational database to eat really efficiently if you set some rules. For example, what utensils to eat what dishes and what order to eat these dishes in. This is called creating indices, and relational databases perform really well when you create indices and constraints. Anyway, I recommend just picking one relational database technology, for example, PostgreSQL, and understanding it really well. Sort of leaning on the food metaphor for a bit longer, NoSQL databases come in a lot of different flavors, which means there are so many different spices, but honestly, just pick the ones you want to learn and learn them really well. For example, if you wanted to learn a vanilla document-based database, just learn MongoDB and call it a day. If you have a lot of complex relationships, including a lot of edges and nodes that define relationships of your data types, pick up something like Neo4j, which is a graph-based NoSQL database, and get familiar with at least one type of key-value-based NoSQL database, for example, Redis or Memcache, because it's going to really help you write caches. Okay, this next section is going to involve a wall of text. There's a lot of words splattered on there. Don't get overwhelmed. They're mostly naming a lot of technologies you're going to be using for your different solutions. We've talked about databases. Let's talk about data warehouses now, because the way you sit people on a bus is going to be very different from the way you sit people on a massive cruise liner. And that's what data warehousing is all about. Now, you're going to hear a lot of terms like data mesh, data mart, data lake, data warehouse, but understand that these are all different technologies to be storing large-scale data in a format that lends itself well to analytics. And the reason cloud engineering is best friends with data engineering, particularly when it comes to data warehouses, is because you simply cannot handle the scale of data ingestion and data storage for big data without using cloud resources. Your laptop would fry up if you wanted to do any of this locally. And never forget, your father is never going to approve of you until you understand data pipelines, because this is the process that takes data from databases and other upstream sources and loads them into a data warehouse for analytics. And much like how you can have so many different ways of food being served to you, you can have a lot of different ways in which data comes at your system. For example, you can go to a sit-down restaurant that is a fine dining restaurant. You can go to a fast food restaurant where food is served to you just like that. You can order food on Grubhub and wait for hours before the food reaches your table. There's so many different ways. And in much the same way, you can have real-time data, you can have streaming data, or you can have data that comes to you in batches. And you need to be able to handle all of these when you're building your ETL process. Now, there's a lot of different ways you can order food. You can order food on Grubhub, on Uber Eats, on Postmates, and at the end of the day, food is going to be delivered to you no matter what. It's a matter of preference which app you want to use. And in much the same way, it's a matter of preference and familiarity when you're picking a cloud provider to work with. But no matter what cloud provider you're using, they should be having a technology for compute, for example, Amazon EC2, a technology for blob storage, for example, Amazon S3, a technology for databases, for example, Amazon RDS, and finally, a technology for the ETL process, aka Amazon Glue. Okay, now we're getting into the realm of McDonald's scale fast food serving, aka using big data tools to handle tremendous volumes of data. And you'll want to learn something like Apache Spark, which is truly a magical tool because it lets you kick off queries against really large data in a parallel distributed manner, meaning you're going to have multiple jobs that run queries in a particular stage, and the results from that stage are going to be synthesized to kick off a batch of other queries in the next stage that comes, and so on and so forth until you get the analytical results that you need. And whenever you hear big data and distributed, you should be thinking containerization and orchestration, and you're able to containerize the processes that are involved in distributed systems using Docker, and then you're able to orchestrate the deployment of these containers using Kubernetes. But imagine you set sail on a cruise ship, and anytime you wanted to add new resources to that cruise ship, the cruise ship had to come back to harbor and restart its journey again. That simply is not going to work. So you have processes called continuous integration and continuous deployment, where if you want to make integrations or add new features to your entire process, there is a clean way to do it while your entire system is working perfectly fine and in flight. All of this works if you're able to monitor the health of your entire system using tools like Datadog and Prometheus. In the world of distributed systems, you're going to have a lot of different systems. Some of these systems will work really fast. Some of these systems will work really slow. But all of these systems may need to talk to one another, and that is where distributed messaging comes into play. A key part of continuous integration and continuous deployment is a way to have a checklist that says, yup, my system's still working perfectly fine. And that is where testing comes into play, and you have to understand the different kinds of testing and the scenarios in which these testing make sense. But listen, at the end of the day, as a data engineer, you are going to have to be responsible as the parent or the legal guardian for the said data. Much like in the world of software engineering, software engineers are responsible for the features they write and ship. You're going to have to be very serious about security, about data quality, and of course, data privacy. And that is it for today's video. You can find this roadmap and many others like this on roadmap.sh. If you found this video helpful, please don't forget to leave a like, add a comment, and definitely subscribe. And I'll see you in the next video. Peace.